Our next presenter from a company that doesn't need a lot of introduction, leading global cognitive solutions and cloud platform company, IBM. Jayant Kalagnanam is the Director of Enabling IoT and AI Technologies. He's also Chief Scientist of Industry 4.0 at IBM. IBM's the largest technology and innovation employer in the world, serving clients in 170 countries. For manufacturing companies, their solutions deliver a spectrum of capabilities that include increasing productivity, output quality, predicting operational failures before they happen, and mitigating supply chain disruption. His presentation theme is how can you apply analytics and artificial intelligence to your factory today. Please welcome Jayant Kalagnanam, and Director of Enabling IoT and AI Technologies at IBM.
Okay, good morning. Thanks for having me here. It's an honor and a first-time experience for me to address this particular conference. So I work at IBM Research back in New York at the Watson Research Center. And I've been at IBM for about 22 plus years now. And almost all my work has been essentially focused at applying either optimization or AI or analytics to heavy industries. So what I wanted to talk about today is, so in a lot of my work, I work very directly with customers, both internally in our own semiconductor fabs, as well as a lot of our clients worldwide. So what I want to take time to do today is essentially sort of give you an overview of how AI is playing into manufacturing, right? We see a lot of discussions about AI everywhere, right? Every day when I drive into work, maybe every other day I hear about AI on NPR and what it's going to do to our workforce. Who are campaigning on this issue, right? However, the fundamental question is a lot of the AI is really sort of motivated in its early applications around social sort of media-related applications. So, this excitement of AI, which is fundamentally changing computer science, how can we use it to do useful things for manufacturing, right? And the thinking that we have, and what we've done quite a bit of, is along this kind of a technology outlook, right? Which is start working and start building self-adapting or self-learning solutions using ML and deep learning, right? But there's an important point here, right? Which is this issue about not just having and using available standard machine learning, but really sort of purpose building it for understanding either physics constraints and or operational constraints, right? That sort of really leads to a whole new class of sort of techniques that we have built out. And the next step is essentially as we harness and leverage the data from across the plant and across assets that are geographically spread out, how do we get a good domain understanding of the data to contextualize it? And here's another field of AI around knowledge representation and semantics that is potentially very useful for capturing data, maybe even more quickly, and developing a domain understanding that allows us to do better reasoning and inference with it, right? And essentially, these sort of approaches allow us to target sort of multiple aspects of improving efficiency, throughput, and continuous engineering. So much of the theme that you'll see as I show you different examples is around building different types of cognitive advisors for different functions, right? And essentially, this slide tries to highlight sort of what is the focus area for building solutions in Industry 4.0, right? And it's highlighted in this blue box right in the middle. And what I want to point out is, there are a lot of different AI and machine learning engines that are available, right? On the cloud and now increasingly on-prem, given data privacy sort of related issues, and several IoT platforms. But fundamentally, what is important is, especially in order to sort of build applications quickly and scale them widely, we need a set of purpose-built machine learning pipelines, right? Which is a common terminology in AI, which is to look at the task sequence required to build and run a machine learning sort of solution, which are targeted and purpose-built for manufacturing and heavy industries. So much of the work that I'll show you is work that we have done towards identifying these purpose-built abstractions, right, based on a lot of applications that we have built out. And I'll show you some examples, like process monitoring, and optimization is a very, very interesting one, and I'll show you some more details on that. Similarly, failure analysis or anomaly detection, or cohort analysis, which is looking at data across multiple assets or fleets of assets, right? And fundamentally, being able to have this sort of purpose-built pipelines or solution patterns is a very, very useful way of quickly bringing a solution and customizing it for a given data set and deploying it. And much of this kind of thinking has driven the work that we have done pretty widely in a lot of industries, right? Starting from process industries to discrete manufacturing, like in the semiconductor domain and in the automobile domain, to process industries like oil and gas, chemicals, to name a few, right? And mining. So and I just wanted to sort of give you a little bit of a flavor of the sort of variety of areas where we've applied this kind of thinking. Like, for example, in semiconductor, the focus often is to sort of improve throughput using various kinds of virtual metrology kind of techniques, which have been really boosted by using deep learning techniques, right? Or looking at heavy assets like air compressors that are used in offshore platforms to do anomaly detection, especially in light of the fact that there's a lot of non-stationarity in this kind of data, meaning there are multiple operating modes, right? Similarly in cement, in aluminum smelting, and so on and so forth. But fundamentally, at the heart of sort of this notion of a solution platform, right, or a sort of a pattern, is this idea where in the center of this slide, you'll see a bunch of different solution patterns that we have identified as the right abstraction that is relevant for manufacturing, right? Once again, if I take the example of process optimization, right, on one side, given a data set for a particular process, either at a unit operation level or data from across the entire plant, there are multiple techniques that one could potentially use, right, which is sort of the collection of what is available in open platforms, along with additional very specific purpose-built algorithms that we've built as well. But the time that it takes to do the trial and error to come up with the right model for a given data set, we've now automated using AI and optimization so that for a given data set, we can really significantly shorten the amount of trial and error required to come up with the best model, right? So that is sort of one aspect. The other aspect is on the left-hand side, as you take data from multiple sources, right, which are also multimodal, right? Increasingly, the use of text data in terms of maintenance logs or repair manuals, coupled with maybe image and video feeds, maybe and other sorts of modalities, as we bring it together, often a lot of effort needs to get spent in that part, right? And that is where building semantics for different industries could give us a really good start in terms of contextualizing this data, right? And from an AI perspective, right, taking data from a domain and automatically understanding the domain, I think is still a grand challenge, right? I wouldn't say that it's done yet there. There's a whole building in IBM research, where a large fraction is looking at these kind of questions. But there are really good, useful tools that are beginning to become available, and I'll show you what we've done with some of these, right? But this is sort of the core theme that I'll sort of talk about as I walk you through a whole set of examples next. This idea of purpose-built solution patterns, right, which are then used to build solutions in different industries. So let me sort of start with a solution pattern which I think is particularly interesting and particularly useful, right? We call this the plant advisor. And the fundamental notion, the fundamental idea that's built in here is that if I look at many of the operations, either in a process setting or in a discrete manufacturing setting, the core unit operation, right, is often monitored and managed and controlled using either empirical or engineering models, right? And it's very hard to actually use real-time data to assimilate it into a full-scale physics simulation model, right, in real time. As a result, I've seen this again and again, people depend on, subject matter experts to be able to look at what is happening and then figure out what is the right thing to do in terms of, say, advisory control, right? And fundamentally, what we've done here is taken some of the available evolving tools to do data ingestion, right, from a particular manufacturing process at a unit level and learn a behavior model very quickly, which can then be used in an optimization framework to provide advisory control in terms of set point recommendations, for example, right? So this is not targeted to sort of change real-time control, right? That remains, but it's a question of, looking out, say, 72 hours or a week ahead, understanding how the system is evolving over time, what is the appropriate set point that could improve performance. And I'll give you a couple of really interesting examples, right? This is work we are doing with a very large oil sands company. Oil sands is an interesting process. It's like it's mining plus oil refining coming together, right? So you have primary extraction, secondary extraction, and upgrading. And of course, if you look at the data across the plant, it's huge, right? You have a lot of tags that you're gathering. And fundamentally, there's a structure to the problem in the sense that there's a process flow sheet, right? And I'll show you what it looks like. As you can guess, it's very big and complicated. The measurements are well over 100,000 tags that are available, right? But fundamentally, going back to this notion that, right, we need to make our machine learning sensitive to sort of structural or domain information that's available to be able to learn an appropriate model which captures behavior either at a subsystem level or at a unit operation level, to then allow for optimization, right? And we call this regression-based optimization. And essentially, what we have done in this context is to sort of handle two sort of issues, right? One is providing recommendations when the system is working normally to basically improve throughput, right? And this is coming sort of from the fact that you have a better understanding and a better behavioral model that is really tuned to the observations in the last few shifts, right, or the last few days. And the other aspect is, if we are not able to run the plant to plan because maybe some capacity went down, right? Often compressors and pumps tend to go down. What is the optimal recovery plan that brings us back to the new normal as fast as possible, right? So this is work that we have sort of piloted and we are deploying, right, on a plant-wide scale, right, with our partner in oil sands. And in fact, for those of you who had a chance to come to Think, they were there discussing this. There are 3 site-wide leads who run the plant shift by shift, right? And they're like, majorly involved in, using the recommendations that are coming from here to do this. Hopefully, you can't read that. But that's sort of a small part of the process flow sheet, right? And essentially what we want to be able to do is to take the data, overlay it on the process flow sheet, to be then able to learn the behavior of any one of the black box subsystems that we draw in terms of our control volumes. And there are fundamentally a couple of really important ideas here, right? One is this question that if I have data from, say, over 100,000 tags, can I use this data in a way where I can sort of wring out of it sort of an understanding of what are the different behavior modes of a plant, right? And thereby look at now in that sort of context what is happening in the last 6 hours or 8 hours on a shift to understand the behavior and what can I do based on reference behaviors from the history of the plant. So in essence, you're asking the question, here's a huge dump of data, give me a playbook that I can give to my plant manager, right? And there are some very interesting techniques from representation learning from AI, which essentially where we take this kind of data, which has a time series nature to it, right? And re-represent it in a compressed form where sort of the temporal trace of the data is compacted to a vector representation, right? Using these kind of autoencoders, right? And these then can be used to provide sort of an analysis such as clustering, and there are many other techniques to sort of identify the behavior modes which are shown by these different clusters, right? And what is nice about being able to do this, by the way, even the compressed representation would not be a two-dimensional representation, right? I'm just showing that for convenience. But fundamentally now, if I look at the last 6 hours, and if it falls in a particular cluster, I can look at sort of the behavior of the neighborhood 6-hour windows in history, right? Which would be an apples to apples comparison to understand, am I in the last quartile or the first quartile in terms of, say, throughput, right? And that gives me a way to sort of benchmark how I'm performing right now, and then we can look at how to sort of mitigate for that to improve performance, looking at controls in that neighborhood, right? So it's a very interesting way of taking a lot of the data and actually sort of getting knowledge and insight out of it, right? And the second part is really to do system-wide optimization for set points, right? And in order to do that, fundamentally, you're looking at different subsystems in primary extraction and secondary extraction and upgrading, right? This is where you get good, you take bitumen and make good quality oil with some buffering through tanks, right? And basically what you want to do is take all the flows and other controls and figure out what should be your set points based on the current behavior of all these subsystems, right? And so this is it's a very interesting optimization problem. Especially because we're going to be using regression models, which, unlike sort of traditional techniques which have derivative information, we have to do some extra work to be able to get that, right? And the other thing is we have 40 to 50, different subsystems. So we have to learn these models, continuously and update them continuously. So we really want to automate it, right? We don't want to be doing this exercise on a daily basis. So we have a class of deep learning techniques that does this, right? That's able to automate this learning in terms of what is the behavior of each subsystem, looking at recent behavior, right? And then conditioned by what we expect the physics or the operational constraints of these sort of subsystems, right? So these two together sort of bring sort of the ability to do both an understanding of how this plant is operating and also an ability to provide recommendations to the site-wide leads, right? And this has gone through at least a few months of validation, and we are deploying it out in stages to the entire plant out in Alberta, right? So I think this is sort of really interesting and really exciting, right? Because it sort of takes up a notch what we can do now with the data in terms of leveraging AI for improving performance. I want to give you another example, which sort of that was a macroscopic example, right? I want to go microscopic, right? Which is, let me take a very complex unit operation, right? And there are many of those out there, right? Smelting, blast furnace, and I can go on and on, right? Semiconductors, where we might have some understanding of the physics, but the simulation of actually what is happening is quite hard to do, right? And on top of it, a blast furnace is it's a lagged process in the sense that you put iron ore, it takes about 6 to 8 hours before it comes out as hot pig iron at about 1500 degrees centigrade, and you're blasting hot air, which takes a few minutes to get through, right? So the inside dynamics is very complex. And the question, it's very, very hard today to take any simulation model, take real-time data and assimilate it to be able to use it for monitoring, right? So one of the things that we have done is sort of built a whole class of techniques to actually learn the underlying dynamical behavior of fairly complex systems directly from data without having to appeal to an understanding of sort of the equations, because we may not have those available readily. I just want to give you a very small example to highlight what this means, right? So this is an example of a chaotic attractor of a system which is well known in the literature. It's a simple one. But basically, the dynamics of this simple system is chaotic, and it's shown in this panel where the black line shows in the state space how the trajectory of this particular system moves, right? And the data that we have are the red dots, which is essentially a very noisy representation of actually the underlying structure, right? And what we've been able to do by building these class of deep learning models is essentially reconstruct the dynamics which based on this noisy data, right? And in essence, what this says is, that again, these class of techniques are doing a really good job of filtering noise and capturing structure for very, very complex processes, right? And you can see the result, right? Because of that, we are able to do multiple step-ahead predictions with very little uncertainty propagating out, right? I mean, typically, if you look at forecasts, the uncertainty goes boom. And fundamentally, this is, again, the reason for that is it's able to filter noise and learn structure, right? And ultimately, it is underlying the structure is physics, right? And applying this back to the blast furnace, basically what I want to show you in this panel is, by the way, the other challenge that we find routinely is for these high temperature sort of processes, the measurements that are available at high temperature are very sporadic compared to the other sensor measurement, which is on the outside of the blast furnace, right? So having to deal with multiple scales in the behavior, as well as having to deal with sort of the sparsity of some of the data. And essentially, if you look at the data, right, the red line shows the predictions that is made by learning from the black observations for hot metal temperature, right? And it does a really good job of getting both directionality and the actual temperature itself, right? And it keeps evolving, right, by moving a time window in terms of learning this, right? So those are examples for building these regression optimization pipelines. Another sort of template that I wanted to show you was on asset management, right? One of the core fundamental issues we see again and again in asset management, right, is you have a lot of time series sort of sensor data that we're getting. What is normal and what is abnormal, right? Simple question, and in fact, one of my VPs always asks me, tell me what is, when things are good and things are not good, right? And although it's a simple question to ask, it's really, really hard to answer, right? Because it's very easy to sort of get misled by changes in behavior of a complex system and tag it as being abnormal. So fundamentally, some of the techniques that we've built out is to essentially look at these multivariate sort of data and sort of characterize structurally what is the interaction structure between the sensors which are being measured, right? And that is shown by some sort of graph like this, and then use that as a reference behavior against which now I can look for changes in the behavior structure itself to understand if there is an anomaly that is happening. These kind of approaches, there are a special class of approaches we have developed called sparse learning, which tries to sort of minimize the complexity of the model while trying to get maximal sort of accuracy in terms of modeling the problem, right? So it has a lot of, the other advantage is it has very good interpretability, right? We can tell you exactly what interaction structure is causing a particular kind of interpretability. But just I want to give you an example of applying this kind of thinking with data that we get from large fleets, right? We call it cohort analysis. In part, there's a similarity with what happens in medicine, right? In medicine, we look at data from large patient cohorts who are all different, because of their genome, because of their food habits, because of their other habits. But at the same time, there are some common principles that we're able to extract and learn from it. Right? And that's fundamentally the idea, right? If I get data from a big fleet of assets, although they might have different environments in which they are operating or different operating conditions, there's something core that we can learn from it, right, in terms of a class of behaviors. And the advantage of doing this, and we applied this for example, data that we get from multiple air compressors and offshore oil platforms. I'll skip this slide. I want to just highlight to you the kind of results that it sort of enables, right? So the basic idea is that I have data coming from different sources. I learn from it like a small dictionary of different types of behaviors, right, that I've observed in this data set, right? And that becomes my sort of behavior dictionary, right? And now for any given asset, I can use that behavior dictionary to sort of come up with a way of parameterizing for that locally and sort of giving a fairly accurate model, right? And we can get into a discussion on this offline as to how to interpret these kind of techniques, right? They are, again, some sorts of complex projections of complex data onto a simpler, low-dimensional space. But fundamentally, what it does is, if I compare these kind of approaches against more traditional approaches, the signal that I get that separates the red, which is the behavior in a pre-failure window, versus the black, which is behavior during normal, is much, much cleaner by doing this kind of analysis than many of the traditional methods here, right? And it comes from the fact that now you have a better understanding of all the behaviors, and you're essentially sort of looking at that entire cohort of behaviors before you make a decision about what is normal versus not. Right? So it's a very interesting technique. We have applied this extensively to actually semiconductor manufacturing and working with some of the biggest tool makers in the business, and it's very promising. But again, the highlight here is it sort of goes beyond using standard machine learning libraries. Right? It really is able to sort of look at the understanding of structure for a given domain at the mathematics itself to incorporate the learning process. And that is incorporated into these like purpose-built machine learning pipelines that I highlighted. There are sort of a couple of other things that I want to highlight. Right? One is going back to this notion of knowledge graphs. So one of the key things in terms of the use of some of the AI techniques to extract information or knowledge out of, say, text or other unstructured data sources, is that it provides us an additional ability to embed domain expertise by extracting it out of, say, maintenance logs, for example. A typical use case is often maintenance logs will tell you, what happened at a particular point in the life of an asset. Right? However, maintenance logs are never at the same place where the sensor data is. Right? So our ability to bring these two together actually sort of elevates the level of analysis that we can do dramatically. And it also, and here's an example of how embedding these kind of semantics also helps us build. So this is sort of a structure that we have learned in the setting of a construction business. And basically, what this structure represents is sort of the different sort of phases of how construction is done and how they sort of impact each other, right? And what is sort of particularly interesting about doing these kind of knowledge graphs is that it allows us to sort of build very, very cognitively interactive interfaces, right, which can understand domain in terms of voice-based interaction, right, where you can probe for data for analysis and build standard stories about what you're seeing in terms of the data, right? And then it also can make recommendations about how to do diagnosis when you're looking at why a project is not healthy or whether it's healthy. Right. So it's sort of another interesting example of the use of knowledge representation techniques, right? So I'm going to finish up with one or two more slides, which is this last topic of reinforcement learning. And the reason why I want to mention this is, again, when we look at media, there's a lot of excitement about how computers are now routinely beating humans in games, right? From Go to chess. And the best part is, right, I mean, in IBM, we built Deep Blue, I think it was 99, we beat Kasparov. But now the latest versions of the chess games use reinforcement learning, right? And in fact, other than giving them the rules of the game, you don't need to give them anything else, right? And you need a simulator of outcomes for a game. And it can learn by itself, and it sort of routinely self-learns at a level where it can beat the best chess player in the world, right? And this is true for many, many games, actually. A lot of Atari games, everything. And at the heart is this idea of reinforcement learning, where the idea simply is that if I have an environment or a simulation where for every action that I take, I know the outcome as being good or bad, right? I have a way to measure it, right? If I have that environment, I can actually do a lot of learning, right? And that's why it's called reinforcement learning, right? And by the way, these problems are really, really hard, right? If you look at sort of the complexity in terms of the combinatorial space for chess, it's 10 to the 120, right? And for Go, it's 10 to the 170. So we started looking at using simulators, right, for manufacturing processes, right, like fab scheduling, which is a very, very complex a stochastic queuing kind of network scheduling problem, right? And see whether we can use these kind of simulators to actually learn scheduling policies for different sort of settings and different sort of wafer starts. And fundamentally, if you sort of think about sort of the commonality between how to leverage these methods that are used for game playing, say in a context where we have a simulator from which we want to learn sort of optimal policies, the basic idea is twofold, right? If I have enough examples that I can either generate from history or from my simulator to learn sort of what is called a policy network, right? Which is if I'm in a given state for a system, right? If a system is behaving in a particular way defined by its state, right? What is the best action I should take, right? And once I have that kind of a specification, I can let the system sort of play against itself, right, with different policies to see how to improve the outcomes. And using this sort of self-play data, you get what is called a value network, which is able to understand for a given state, what is the value of taking different policies. And essentially, what I've sort of laid out, and I think there's a little bit of detail here that I don't want to go through, but essentially, some of the techniques that come from reinforcement learning coupled with a lot of the work that we do with constraint optimization methods and derivative-free methods, right, which are able to better handle the details, right, of constraints and physics, we can start to learn to build new ways to learn optimal policies for manufacturing processes and plants using these kind of simulators, right? And there's a slight wrinkle in the discussion, which is a lot of these game-playing simulations are very, very fast because they're very simple, whereas our simulators tend to take a lot more time. So we've sort of started to build out a whole new class of techniques in terms of what are called explore versus exploit kind of techniques to better handle those things. Something here says time is up, so I'm going to take it seriously. So I'll stop there. Maybe there's a couple of minutes for a few questions. Yeah, Sudesh.
Fascinating stuff, and I have a question. I have a two-part question. In the industry that you primarily covered, there's lots of sensor data that's available, and all of the sheets that then describe the process. But if you look at processes that don't have the luxury of sensor data, how do some of these experiences of yours can help an industry like that? And the second part question is, in terms of raw impact, how would you define, whether it is in this example or others, even in the mining example or shale gas, how would you describe the value that you've been able to extract out of these initiatives?
Okay. Let me answer the second question first. So Yeah, so it's thanks for asking. I should have probably highlighted that in my talk, right? So typically, if you look at the oil sands example, our expectation is to improve throughput, right? Measured throughput by about 500 to 1,000 barrels a day, right? You can, sort of tally up the numbers on that, right? So you're talking about tens of millions, right? So on a big manufacturing plant, right, improving efficiency. So for example, when we were looking at smelting, we were trying to improve energy efficiency by about 0.5%, right? Now you're talking about a 25 megawatt plant, right? So essentially, I would say a lot of manufacturing processes are, of course, quite efficient, right? They've been around for a while. So the key question is whether understanding the behavior more precisely and more locally in terms of what's happening now or in the last few hours or days allows us to get that extra percent, or it depends in cement grinding, right? Which an example that I didn't show. It's again an energy efficiency question, right? We were able to improve efficiencies of about 2 to 5%. Okay, it depends a bit on if the plant manager has a lot of experience, they tend to do a little better than if they don't, right? But typically, those are the kind of improvements in efficiency, right? Now, and going back to this question of if you have no data, right? So, of course, AI and machine learning is really data-driven learning, right? And in fact, a lot of what I talked about is how do I best leverage data, right? Now, the last parts, especially, I saw some of the examples that you showed in your video. They were really fascinating, where you use robots, right? A lot of the reinforcement learning kind of techniques are particularly effective for robotic planning, right? Because there, the simulation is very easy to do, right? It's a simple planning problem, right? And it's routinely the standard go-to example for doing reinforcement learning. Right. Now, the only thing is, again, a lot of the reinforcement learning is done in the context of autonomous vehicles or autonomy, somewhat sort of different constrained way, right? It's more like navigating a road or a room, whereas when we're looking at manufacturing, the kind of constraints that we need to impose are a different class of constraints, including safety, for example, right? And we have a really interesting example where we taught a robot, right, trying to fit like a peg into a specific shape by basically trial and, by self-learning, where it tried a lot of experiments to finally figure out, right? And of course, the key is how many experiments do I need to do to get it right? And you want to minimize that. So we've sort of paid a lot of attention to what is sort of the optimal path to get to where you need to in those kind of conditions where you can do experiments or you can do simulations in lieu of data. Okay. Yeah. That seems one more question.
Have you found any opportunities for smaller manufacturers who may not have, someone of your caliber on hand to improve throughput in any fashion, either using machine learning or just out of an aha moment you've had from these experiences? I'm talking, a $10 to $100 million manufacturer.
It's a good question. So I personally don't have that experience. I've largely worked with very large companies. But so much of the work that I show, is being funneled through our products called Watson IoT Production Optimization. And in that context, we have, started to provide these purpose-built pipelines to a lot of the partners so that we can go build out for, small to medium businesses. So yeah, I think that would be a very interesting discussion to follow up on, right? And I can help connect with some of the folks who are, essentially trying to answer that question. Yeah.
Just have a quick question. What about the human side? How do you get engineers to buy into this? Because, people only have a little bit of experience with it. It can go horribly wrong, as you probably know. Right? It can confuse in ways that a human expert never would. At the same time, as you just pointed out, it requires a lot of expertise to support it, keep it going.
Yeah. No, that's a very good question. So we fundamentally have taken an approach, especially in IBM, with regard to AI, is that a lot of the things that we build it as advisors, right, rather than as full automations, right? So for example, in the oil sands example, we have all the 3 site-wide leads working with us directly to influence us in terms of what are the kind of things they're looking for in terms of recommendations, right? And ultimately, it took us 2 months of validation, right, where they were using the output before they were willing to sign off on it. So fundamentally, the way we build these systems is to provide recommendations sort of at the right level, which matches what they are trying to do already, rather than trying to automate any of it, right? And I think what my expectation is that if we involve the stakeholders in the discussion very early, right, in that sort of framework where they're essentially going to get another advisor that, I mean, if you go back to the oil sands example, right, currently, they have a lot of data that, on which they're trying to do some mental math, right? So they're quite aware that they can't do all the mental math, right? And so in that sense, they were very good at pointing out what are the kind of things the system needs to be able to, sort of give them a good way of summarizing to understand what's going on. So there's no easy answer to your question, to be very honest, right? But I think having the people who are going to use it part of the process early on, I think, has helped us every time. Okay.